So what we're going to see at this lecture, so today is a full GPU day. I'm going to start by the basics about what is a GPU, why do we need a GPU, and going to CUDA and the basics of CUDA and how you basically interact with a GPU with CUDA. So I'm starting to see really the basics of what is a CPU and what is a GPU, what's the main difference between the two, and when do you want to use a CPU, when do you want to use a GPU. Then I'm going to explain a bit what is CUDA, then how basically any code handle the GPU. So how do you interact basically with the GPU? And basically the first example on how to code to CUDA. After that, we'll have a bit more advanced code on OpenACC. And this afternoon, you will have lectures on how to optimize the CUDA code at full efficiency. Okay, so a very simplistic pictures of one CPU here and one GPU here. In green, you have the computing unit, so that the silicon part that's actually doing the computations, multiplications of integer, multiplication of float, of double, and stuff like that. In pink, I would say, or red, depending on how you want to see this color, that's everything which is related to memory, so that's where you store the information. And in orange, you have all the control units, so you decide which data needs to move and stuff, all the logic stuff associated to that. So the big difference is striking. Here you have a lot of memory and big control. Here you have basically only computations. That's the big difference between CPU and GPU. So on CPU, you have a couple of cores. I mean, you can go up to 64 or 128, even with hyper-threading, but let's say relatively small numbers. Here you have a lot. We speak about thousands, tens of thousands of cores. The difference is that here, everything in a way is slow. Here, everything is fast. So you have a lot of control, so everything's go extremely fast. So data arrive is handled directly and is released, and you will take the next. While here, in a way, everything, you take a lot of data together. So that's what I say, it's slow. You collect a lot of data. Then you handle all those data simultaneously. That's why you actually, at the end, are much faster. And then you move to the next batch. So in a way, everything here is slower, but you do so many data at the same time, then you can handle and gain in terms of speed. So that's really for a high number of data that you get. So in a way, CPU is what we call low latency, and GPU is high speed. So that's why I like to see this example. So the speed is really the number of operations per second. You can take your basically internet connections. That's a perfect example. When you want to see a movie, what you want to have is a huge bandwidth. That's what we're interested in. If you want to check one website, the bandwidth is completely irrelevant. What matters is the latency, is the time basically to make the connections back and forth. And that's what's really important when you go to a simple website. And CPU basically try to have this number as small as possible. On GPU, you have one big latency, but you have a lot of speed. The speed is much higher. So one example I always give and I like is how to transfer data from one cluster to the other. So there, the amount of data to transfer is not a single USB. It's basically a lot of disk. And what Amazon is proposing is basically to send to your cluster truck full of disk. Then it connects a lot of cables, directly fiber cable directly to your cluster, move all those data then super fast because it's not internet, it's really a lot of fiber directly going to your cluster. Then they unconnect everything and move the truck to their cluster and move all the data in other directions. So you can see obviously the latency is super huge because the latency is the time to move the truck from their cluster to yours and then going back. But the speed will be super good. And I don't know if some people know that some of your colleagues may have run on Zenob a couple of years ago, a couple of months ago. So we closed Zenob and opened Lucia a couple of months ago, and we had to move all the data from one place to the other. And basically all the people, what they were doing, they were putting disk, send it by car to put all the data on the disk and doing data as well, which is much faster at the end of the day than using internet. Simply because, yes, the latency is huge, obviously, but then the bandwidth here is much larger. So latencies, in a way, is reactivity. And I said GPU is not reactive, so GPU are slow to answer. Really. So the first question is, of course, if you have high latency, it's not that great. That means it's not super fast. So how do you handle that? Just to warm up, basically, right? Do you want to not use the GPU in that case? What you want to do is to do multitasking, so do basically something else while waiting, or you pay the price, but okay, in any case, GPU is faster. So what do you think? If you don't know, pick one, right? It's you just will be a bit interactive. Okay, yes, that's the basic idea is really that. So if we see here a CPU code, we have 4 tasks to do. We do the computations, then we wait a bit for the data. That's this white stuff which is waiting for the data. Then do the computations, then wait for the next data and so on, and then move to the next task and so on. On GPU, basically waiting for the data is much, much longer. That's what you can see here. So basically what you do, you overlap the 4 computations so that at any time, so that's slicing in time. At any time, your GPU is doing 1 computation, sometimes in 1, sometimes in 2, sometimes in 4. And basically, you never have the time where the GPU is not handling a data while still waiting for the other data to arrive at the GPU. So that's what we say, that we need a massive amount of data on GPU because you have a lot of cores. That means you need a lot of data to basically be handled by the GPU. On top of that, you need to scale the number of data paths so that you can do this overlapping efficiently. So that's why GPU is really for a massive amount of data. If you want to compute the computations of 20 numbers, stay on CPU, it will be much efficient. If you want 20 millions, then GPU might be a good idea. And to make that in context with my truck, basically the idea is to not having a single truck, but basically a lot of trucks doing the transit. What is important is that at any time in your cluster, you have 1 truck taking data. And probably here as well, putting data in another cluster. The number of trucks which are in transit here is at the end completely irrelevant in that case. Okay, so this is a plot that Damia will show you at least 1 or 2 times. So that's the Adam laws. So what do you can expect in terms of speed when you go to a GPU with, let's say, 2,000 cores? And of course, this depends really of the program that you are running and how much of that program you can move on the GPU. So if your original process actually was 2 independent parts, A and part B, and then you can make B much faster, of course, in this case, it will not change that much, simply because A is the dominant part. But that we've seen multiple times is how much you can gain, and that's a simple rule of thumb. If you have 95% of your code that you can parallelize, the maximum you can get is basically a speed of 20. So you are quickly limited in a way like that. Yeah, let's just check that you have understand the Adam's laws. That basically means that you have to work a lot. So it means that the gain in GPU are limited. Optimize the hot kernel. What I mean, hot kernel is the function that takes most of the time. That's what I mean by hot kernel. But that is difficult to keep the GPU busy. Let's check your answer. Actually, let me check how I put. So actually, the gain on the GPU, in a way, yes, the 3 are true in a way, I would say, is limited. That means you need to work more because the main functions typically you need to parallelize most of your code at least to have a huge gain. And it's difficult to keep the GPU busy because you need to have so many data. On top of that, you don't need to be blocked by the stuff. So to give you one example, we'll go back to the next slide after. So this is a physics code. You don't care about the physics at all. And do you know this kind of plot? It's a flame graph. So it's basically that's time and horizontal each. I mean, this means that these functions takes around, let's say, 10% of the total time. It's not sequential, so that means it can be equal at the beginning of the program, at the end of the program, stuff like that. It's just stack, and of course, you have here the stack dependencies or that function is equal. And what I did on that particular program is that you see that I put some in pink. 95% of the code, 95% of the code is in pink actually, and that's the part of the code that I moved to the GPU. All the rest I kept on the CPU. So this is completely that plot is a flame graph on CPU, and then I move all those pink on GPU. That is the output. So obviously completely different. All those pinks now are in this huge column, and you see that basically I convert 95% of my code into 5% of my code, which means my code was around 20 times faster, which is a theoretical limit. And in a way, it's good and bad. What is bad is that I'm only using my GPU 5% of the time. So the system administrator will not be happy because basically I'm not using the GPU anymore. But I'm 25 faster, so all my physicists colleagues are more than happy about that. And what is cool also for me as a physicist is that all those codes, I never care about it because it was basically 5% of the code, right? So that's code where you say it's pointless to try to optimize it because basically we never see it. It's not important. Now moving to GPU, you see that's the main part of the code, and there are a lot of optimizations possible there. So in practice, comparing a CPU and a GPU, it's not apple-to-apple comparison to my point of view, because you compare one chip that can cost sometimes 500 euro to a chip that can cost 10,000 euro. So if you say, of course, oh, the 10,000 euro machines is much faster, I hope so, because you pay much more, obviously, right? So it's not fully fair. So there are typical different ways to compare them. One way is to say I'm taking a full chip on CPU versus a full chip on GPU and make the comparison, which is, as I said, not fully fair to my point of view. Another one is to compare in terms of cost of electricity. So what is your performance per watt, which is a more fair comparison, I guess. Because at the end of the day, I mean, you don't pay, and actually it's a university here that's pay for all the infrastructure and electricity. But there's two costs, of course, when you buy a machine. The cost when you buy it, which can be large for GPU, more than 10,000 euro. But it also all the electricity it takes years after years, and that's actually much more money at the end. But basically, if you take a full CPU versus a full GPU, the normal speed up that you gain is something like around 20. 10, 20 as normal denominators. You will see people, and maybe even me, in a couple of things saying, oh, we can go 200 times faster, but typically that means you cheat a bit in the denominator. One thing which is important is the clock speed. You can see here the clock speed of GPU is much smaller than the clock speed on CPU. And that's why even if you have so many cores, the speed up are not that great in a way, because everything's run slower. Okay, so yeah, all right. So what do you need to do in order to use a GPU? What is the main idea of the GPU? And that's some idea that we are already seen in previous lectures, actually, is to handle multiple data, but doing the same operations multiple times. So in practice, what you want to have is a huge vector. It's called here input stream, which is super long, which has a lot of data. And you apply on each element of that vector the same operations that we typically call the kernel. So in this case, I'm just updating each value by 1, and that is my output. A very simple kernel, obviously, in this case. But that's the idea. A lot of data where you apply always the same operations on that. Okay, so this is something you can also use in a way on a single CPU. So I'm going a bit away of GPU for 2 minutes. So the normal way, or where I think about the CPU is this. So you have your instructions here, you have your data here, and you have your output. So that's a normal way to use a CPU, and that's a waste if you do that, actually. All CPU can also work in this mode when you have one instruction multiple data. I mean, multiple that can be up to 8 in double precisions, up to 16 single precisions. So it's not as massive as GPU, but basically the same idea of GPU. And then you have multiple outputs. And all CPU have that mechanism. So if you find me a CPU that doesn't have that mechanism, it should be a super old. I think it started in the 90s with that mechanism in CPU. So all CPU have actually that mechanism. And what is important is that basically going from ear to ear doesn't cost anything in terms of speed. So in this model, you have exactly 3 times, you are exactly 3 times faster than this. In fact, it's a bit less, but it's extremely close to that. So just to prove you that's actually the same code as before. Again, you don't care about the code. And here I'm using a CPU, which is a quite high-end CPU, which are 32 cores. So that's the dashed line here. That's the number of cores available. And the normal computations, so if I don't use single instructions, multiple data, which was actually the old versions of the code, is this blue line. So of course, if I'm increasing the number of cores, I'm increasing actually the throughput of my program. So the higher here, the better my code is. And of course, it's relatively linear, not perfectly linear, because the more I ask on my CPU, the lower the clock speed is going to be. And therefore, that's why here it's not 32, it's more close to 25, actually. But basically, the more data I ask him to do, since he has 32 cores, the faster my code is going to be. Going higher, in principle, I can use hyper-threading on those machines, so I can go up to 64. You can see here that there's basically no gain at all. If I start to ask even more tasks, there's no gain at all as well. Now, if I switch this flag, saying, okay, now you can use single instructions, multiple data, because my code is ready. If you have an old computer, so that's the orange line, that's simulating what I call an old computer, something like 2004, 2008, 2004. So all your machines have this one available, and that's just a factor of 2. So instead of doing 1 data at a time, it's doing 2 data at a time, and you can see that it's much faster. I'm not going to through all the line, but if you go, you have the latest, let's say, CPU, the most powerful, you can go up to 8 double precision. So this is in double precision, that's why the maximum is 8. And then you go to this purple line, which is, of course, much faster than this. Not exactly 8, but it's very good. So I like this part because it really shows that it's independent of the number of threads, basically, that I'm asking on my CPU. And that's a huge speed up for basically not no cost, but close to no cost. So that's more, I would say, even before thinking about going to GPU, that's the first thing you should do with your code. And what is nice is that doing that or doing the implementations I will show you for GPU is actually the same. So what is important is data parallelism, to be able to do multiple computations on different data, but the same computations. And that's what you need here for the CPU, and that's what you need for the GPU as well. Technically, if you can do this, you can do the GPU. The opposite is not true, because this is more restrictive in a way. Because here it's really super strict, it should be the same computations point. On GPU, they are a bit more flexible. Okay? So let me go back to GPU. Basically, there are different languages on which you can code for GPU. The most common one, and that's also because that's the most common GPU, is CUDA, which is only restricted to NVIDIA GPU. And that's basically the GPU that we'll find close to everywhere, but in big HPC cluster those days, I would say. You agree on that statement, maybe? That you find NVIDIA everywhere, but on big HPC cluster? No problem. Yeah, that might be problematic. But at least you answered to me, right? I didn't answer to you last time. Okay, so that's an old program in a way. So it started in 2006. At that time, the GPU was much more smaller than they are today. Today, they are completely big, much more flexible, much more memory. Coding at that time was really tough. So what is, let me check the next slide now, okay? What is sad in a way is that, of course, it's related to only one vendor, but it's obviously the advantage is super optimized. The advantage, what my hope is that in 10 years from now, we will not have to speak about CUDA anymore, and we all go to more standard codes like OpenACC that we will learn after these lectures, or my real hope is standard C++. But we are not there yet, and people are not sure it's going. But for the moment, each manufacturer, there are 3 manufacturers for CPU, for GPU. There's NVIDIA, which is using CUDA. There is AMD, which has IP, which is the same as CUDA, to be honest. Just you replace IP by CUDA in your code, CUDA by IP in your code, and everything will work. And then there is Intel and SQL as the main language. So why do you want to use CUDA? So there are 4 propositions. The first one is it has both C++ and Fortran interface. The second one is supported by all GPU. It's evolved as fast as the hardware and is the most popular language. So what do you think is true? I think you can answer more than one answer. Actually, there are more than one which is true. Yes.
Doesn't AMD also have Broadcom?
Which one?
I think AMD also has your API called Broadcom.
Yes, I know RockM, but it's the same as it, no? Or what's the difference? Don't know.
Yeah, I mean, IP is the main language of Broadcom, but Broadcom also includes the OpenACC runtime.
Okay. Yeah, I mean, they're related, let's say.
The OpenMP offload compiler, I mean, Broadcom is a...
Yeah.
It's more like the NVIDIA HPC.
Okay. Okay. So my solutions, I would say. So it's actually possible, and 8 of you know or guess. So you can code CUDA in both C++ and Fortran. So today I will only speak about the C++ interface. I never touched the Fortran interface. I would say Fortran is slowly dying, which is probably good. So I'm only speaking the C++ interface today. But the Fortran interface works and it's still maintained, and you can obviously use it, but I'm not covering in this lecture. So it's technically, so since it's developed by CUDA, as soon as they create a new GPU, they typically include new features inside CUDA to use at maximum the GPU. So it's evolved actually as fast as the hardware. Each time you have a new GPU, you will also have a new CUDA versions to use that particular GPU at maximum capability, which is also the bad stuff in a way, because that means other code, other interface that can try to use the GPU typically have a lag, basically. If you want to use standard C++, will never be able to use the latest options of the GPU. It's a bit like Intel has its own compiler, which is always officially the best, but you need to pay a lot for having it. CUDA is free, but basically that's the issue. And yes, it's the most popular language for GPU, simply because the NVIDIA is selling the most number of GPU, basically. Okay, so let me try to convince you that you need to use CUDA and not something else. Orion, close your eyes, answer your ticket, that's good. So this is not a comparison that I did. So this is a standard operation, so matrix multiplications and update of a matrix. And it's a comparison done, if I'm correct, by a CUDA expert. So I would say there is likely a bias towards CUDA on those. I will show another plots later. But it's clearly let's say a bias towards CUDA. But basically, and it's a couple of years old. So that's all the thing. Don't take that too seriously in a way. But you see here that CUDA has super large efficiency. If you go to other type of code, like OpenMP, OpenACC, and you have terrible results in a way. So you can probably say it's probably better, to be honest, OpenACC and stuff like that. But still, in a way, for the moment, the implementations is actually heavily dependent on your hardware, and you need to use the compiler to associate your hardware. You will not get full efficiency for the moment. My hope, and they say, so the CUDA person that showed me this, say that standard C++ is going in principle to reach this level in the C++ 26 standard. We are not yet in 26, so it's probably not yet released. But the hope is basically for them at least to push more and more to standard C++ to be basically on par at this level. And I guess when that will be the case, OpenACC and all the other will be basically on par as well. So that's what I say. It's my hope is at some point we can get rid of CUDA but I would say it's not yet the case. Yes?
Yes, just a question of terminology.
Yes.
What does CUDA stand for?
So CUBLAS is a dedicated library inside the CUDA language in a way, which is based on BLAS. And that's basically like on CPU. You've seen the BLAS lecture with in the previous lecture. So that's which is basically dedicated to do this kind of computation super efficiently. So that's I mean, it's basically a library designed for this kind of computations. And QPy is actually using CUBLAS under the hood. And that's why you have very, very good efficiency there. So it's basically, I mean, you have a lot, CUBLAS is a lot of functions that's saying you, oh, if your function is symmetric, then use this function, that, and that. So those are super optimized library to do this kind of linear algebra computation. Okay, so where can you find some GPU? So we have quite a couple on the CC. So you have on Dragon 2, you have 2 NVIDIA V100. On Namur, you have what I would say gaming type of GPU. What I mean gaming is that you have, I would say, 2 types of GPU. The GPU that can do double precisions that are super expensive. And that's, for example, the V100 here. And that's, I would say, good for simulations in a way. I'm using it for simulation of energy physics. You can do simulations of materials and all those kind of stuff. That's where you need double precision, so you need accuracy. Gaming GPU, in context of HPC, is of course not for gaming. Those are more for machine learning. So machine learning typically is doing on single or half precisions, and that's where those GPU are useful. But if you want to do hardcore simulations with double precisions, if you need double precisions, then you need to go to those machines. Because doing double precisions on that type of CPU is super, super slow. Because they are emulating actually the double computations. So of course, now we have also Lucia, which is a big cluster with, I put many, but I don't know, a really large number of A100, so more than enough. And then now we have also Lumi. For that, you need, of course, a project, which is not CUDA, which is some AMD MI250X. And for that, you need HIP. But as I said, actually, I propose, there was 2 years ago, a lecture on how to move code from CUDA to HIP. And I proposed mine, actually. And what they did is grep replace CUDA by HIP, and then it was running. So it's, except if you use advanced stuff, obviously, but if you use relatively low level, let's say, API, the HIP API exactly the same as the CUDA API by design, actually. If you need to have something that runs on everything, then you need to use abstractions layer, OpenACC, so very good. Otherwise, SQL, Cocos, Alpaca. There's different code that basically abstract for you the GPU, and then another hook call the correct functions for you. Okay, this I will skip, I guess. Just that on any cluster, you can basically print with sinfo. What is important is basically those arguments to print the resource. It's not there by default. To basically print the GPU and the type of GPU you have available. One thing I didn't mention is for people from UC Louvain, because I guess there are quite a couple of persons from UC Louvain. Yes, we have also Manback, which has something like 30 GPU, and on both sides. So some are gaming, some are HPC grade. So you can basically find everything you want there as well. Typically, my advice is to run interactively at least the first time. So you do this --PTI bash. You have all learn slurm. You ask for the partitions with GPU, and you ask with one GPU attached to it. So in this case, I ask explicitly a Tesla V100, and I ask one Tesla V100. And to test that indeed you have access to the GPU, NVIDIA SMI, and then you will see the outputs. If you don't have GPU, you basically have nothing or 0. Or otherwise, we'll see how many GPU you have access to, which in this case should be 1. Okay. And then obviously, the trivial statement, you need to do a modulo veil to check what are the languages that are being compiled for GPU. So most of them will be with a suffix CUDA as a CPU. Okay. I guess it's not important. This is the same. One thing that can be interesting, but I will skip also quite quickly. So on the latest, or it's not the latest anymore, starting from the A100, which is relatively recent GPU, you can technically split your GPU in sub-GPU. So it's more convenient for you. You can ask, instead of saying that you're coding one big GPU, you can partition your GPU in 7 small parts. And it's like if you have basically a cluster of 7 GPU for you. That's a possibility that you can do. And you can even, in man-back, you can do that on the fly, but okay. Okay. You're still awake? Okay. So a GPU actually is not like a CPU. You don't start a code on GPU. What you always have is a CPU attached to it. So you run your code on the CPU. So your program starts on the CPU, so like normal for you. And then the data are basically prepared typically on the CPU. What is your starting point is start on the CPU. Then you move your data to the GPU. You do your parallel work there. You report back to the CPU. You do that as many times as needed. At some point you quit. But basically what is important in this plot is the GPU is a co-processor. So you start a program on the CPU. You do your stuff on the CPU, and then you do that as many times as you run, and you end. So sometimes a bottleneck for the GPU might be the CPU part. So sometimes you might want to have this CPU part running on OpenMP, for example, on a lot of threads, such that, for example, these parts are fast enough. And the second thing that you can do, but it's probably a bit advanced, is that while you run on the GPU, nothing prevents you to do some computations on your CPU as well. That's the best way, obviously, is to compute on both sides simultaneously so that you don't waste basically your CPU. Okay. Now some naming, because it will be important later. The CPU is called the host, and the GPU is called the device. Just have to know that, nothing important. The functions executed on the GPU are called the kernel. I already mentioned kernel before. That's basically the functions that you run on the GPU. And yes, that's important. You will learn in a way that's the boring part in a way of GPU is actually that you have to manage the memory. So you have two memory, or you have two devices, I mean two machines, one CPU and one GPU, and they all have their own memory. So one have the RAM, one have the cache for the GPU, but they are physically separated, at least for the current moment. If you have seen the Mac with those M1, they now have the same memory, so they share the memory between the host and the device. But that's not yet the kind of machine on which we run, and I'm not sure we are going to go on that direction for HPC in a short term, I would say. So typically, you handle manually the memory management, even if, and I'm not going to cover it in this lecture, it's also possible now to let CUDA manage that for you, saying, I have some data that can be accessed both from CPU and GPU, and you let the compiler basically decide when to move the data. So that's also possible, but I will show you the manual way here. Okay, so these kind of the same pictures I showed you at the beginning, but this is now real pictures, let's say, I'm not sure pictures, but at least real diagrams from a V100 from NVIDIA. And you can see all the components. And that's the same color coding, is it? I'm not sure. So in blue, you have the memory, and in green, you have the computing part, actually. You see a lot of green. So let's focus first on the memory. You see you have a lot of memory. You have a lot of cache here. So that's the L2 cache. And actually, the biggest memory is here on the side. So now, actually, this memory on the side can go up to 80 gigabytes. So it's actually quite sizable. It's not that small. But the number of computing units is more than 2,000 as well. So you have to share that with a lot of computations, obviously. But otherwise, for each computation, the size of the memory is relatively quite limited. The second part, interesting, is what we call the streaming multiprocessor, and that is this red box, and you see we have a lot of copies. So in this case, for the V100, there are 84 copies of that. On the A100, I don't know, I think it's even bigger. So you have a lot of basically independent computing units, actually, which has its own memory. You can see it here, here, and here. And we come back to that a bit later. And distributed computations. And here you see that you have this part, which is for float, and this part is for double. This part is for half precisions mainly. I'm not exactly fully sure when you can use tensor. You can use tensor in other cases, but it's mainly for half precision, and this is for integer computation. So one thing I never understood personally is why, if those are physically different type of silicon, why you cannot use them simultaneously. Looks like you cannot. If you either use the float or the double, you cannot use at the same time. Don't ask me why. I never understood why. You know?
I think it's because you have to power all of this together. You can do climate change.
Yeah, it should be something like that. Yeah, for consumptions or heat. Yeah, I guess. But basically, when I see that, say, oh, both of them together, right? Okay, so the question is, why do you not always use double precisions? Single precision allows you to be twice as fast. You see, you have 2 times more blocks. Some GPU doesn't have it. We should use half precisions, or quadruple precision should be actually what we should use. Just a pretext questions, actually. So yes, single precision in this case allows to be twice as fast, which is a bit different from the CPU. So if you use a CPU without single instructions, multiple data, there is no gain to go in single precisions. So if you use a normal CPU and you don't have this structure of your code to handle single instruction multiple data, go to double precision, it's safer. With single instructions multiple data, there you can speed up your code by a factor of 2, because basically what is limited is the size in range that you can pass to the CPU. And since half precisions, single precision takes less space, you can put more data together. So for CPU, typically, except single instruction multiple data, single precision has no sense. Of course, here it has a sense, you go twice as fast. Issue, of course, some GPU doesn't have it, so you need to have very expensive GPU in order to handle double precision. So if you can avoid it, it's better. Actually, I would say that we should use half precisions, and that's what they do for at least machine learning. But if you can use half precisions, it's good. I'm a physicist. I know that already single precisions, when you say that people are afraid, half precisions is, of course, even worse. If you can use it, you can gain a lot, obviously. And quadruple precisions are some, I mean, I'm using quadruple precisions of my code, but those are not running at all on GPU. And they're even terrible on CPU, to be honest. But sometimes you have no choice, obviously. But you should avoid it as much as possible. Okay. So one thing for the moment, I said, oh, we have this vector of data. And basically what we want is to have this, each data to be handled to apply the same functions. And that's what we call the thread here. So that the thread is basically one unit that is going to take one data, going to do the kernel, so the functions, and update typically another vector. That's one thread. And we have typically thousands of threads available. Now the computations will be organized by block. So that is the combinations of threads that can go up to 2048 in practice. So we can have in each block up to 2000 threads. So each block of thread will be run completely independently. So you can have no synchronizations, no communications, all the stuff that you have learned actually this week for OpenMP cannot be applied between 2 different blocks. So those will be completely handled separately, technically in any order also. So the order of the blocks are not fixed. While within a block, there you can have some synchronizations if you want, message between the thread, wall time, all the stuff that you've seen basically last week are available within the block. So the idea of the block is basically scalability. So you have all your computations, and we call that a grid. So for the NXP thread, we have thread block, and now I say the grid is basically a list of blocks. And you say, that's my computations, block 0, 1, 2, 3, 4, 5, 6, 7. And then when you go to one particular GPU, let's say it has 2 streaming multiprocessors, so that you need computations that you've seen in previous slides. Then it has streaming multiprocessor 0, streaming multiprocessor 1, and basically this one is going to be 4 and 4, as simple as that. Or if you run on the other GPU, where you have more computing units, in this case I put 4, then simply each of them will only compute 2. So that's allow you basically to scale relatively easily from one GPU to the other. Okay, one more thing on hardware. So we have seen the thread, we have seen the block, and now I'm going to see the warp. So the warp is actually within a block. A warp is exactly 32 threads. Exactly 32 threads. If you go to AMD, they call that wavefront, if I'm correct, but probably you're going to cover that, and that's 64. And that corresponds really to different chip, the structure of the chip on the GPU. And what is important is that they are working in lockstep. So for those 32 threads, they will do exactly the same computations at exactly the same time. So there is no way that to say, oh, wait, that one is finished and stuff like that. They do the computation exactly at the same time. So one issue is an if statement. So let's imagine my code here. I have an if statement if x is smaller and bigger than 0, and x is a data, so that it can change from thread to thread, right? So I'm evaluating first that if statement, and I have some of them which are true, some of them which are false. Since my code needs to run exactly the same instructions on all the data at the same time, what the GPU is going to do is to hide some thread. So in this case, it will first going to execute the true statement, and therefore will just mask those data so that it doesn't do the computations on those. So here there are basically no computations possible at all, up to the time that the true statement has been evaluated for those 3, and then the GPU compute the other, and then in this case, those 3 doesn't do anything, and the other ones are working. So why it can be a problem is basically if you have an else statement which is super long, and it's quite rare, for example. Because then you have basically most of your threads that doesn't do anything, and that means a huge waste of time, and waiting quite a lot of time that basically one thread is doing something. So that's why we say that we need to try to avoid basically that, at least by 32 by 32, that the code is doing something slightly different. If you are successful, that's what I do in my code, to enforce that 32 by 32, they are always true or always false, then you know basically that only the true statement will be evaluated, and that every chip, basically, every thread is computing at the same time. And then in that case, the false will never be evaluated. So that's the trick I'm using, is forcing my code so that the data are always positive, in this case by 32, and always negative by 32. That's what we call thread divergence. It's not, if you have 50% of the, if it's really random 50-50, it's not too bad, it's a factor of 2. Otherwise, it can be problematic. Okay. So I have 2 questions, because I introduced a lot of nomenclature, which are all related to hardware. So sort me those elements from the smallest to the biggest. So what is smaller in terms of computing units? Is it the thread, the warp, the block, or the grid? Okay. So 3 answers. So thread, warp, block, grid, that is the correct answer. So thread is 1 computing unit, warp is 32, a block is up to 2000 something, and the grid is a collection of blocks. So that this is the correct answer. So this is not too bad. It's just that those two are flipped. Technically, you can have blocks which are smaller than 32, but that makes really no sense in terms of computing. And now, basically the same questions, but now how is it related to the hardware or to the computing in a way? So here you need to associate them. Okay. So so a thread is indeed handling one data at a time. That's correct. A grid corresponds to the full GPU. That's correct as well. The warp is in thread lock execution. That's correct. That means all the data in a warp will do exactly the same computations at the same time. And the block is going to be matched on a streaming multiprocessor, so on one computing unit, which has multiple warp available. Good. So I guess we cannot all read this. So now what I'm going to do is to port my code to GPU. So what that code is doing, I don't know if you don't read that particular slide. What my code is doing is this. So I have a vector X, a vector Y, and a number A, and I'm updating my vector Y to be A times X plus 1. That's what we call SACSPI. It's a very standard computation pattern. I was thinking, let me try to zoom a bit, I guess. Be able to zoom. So this is the main functions in CPU. So at this stage, everything is in CPU. So what I take is I take two arrays that I pass as a pointer and updating with a for loop. So I guess the next slide. No, but here I'm doing a for loop over all the elements of my array and updating like exactly the formula I was showing before. Inside my code, I'm doing allocations. So in this case, I'm doing dynamic allocations so that it's clearer for the CPU. You could do static allocations as well. So a malloc. And yeah, here I said that already, that I'm doing the for loop. So I'm already giving you a bit the answer in terms of speed. This code is actually not computing intensive, but it's more memory intensive. So you basically have to move a lot of data forth and back, and therefore you are basically dominated by the bandwidth of the GPU. So how much you can move data from your CPU to the GPU. So that's why in this case, you can see all the code is basically the same efficiency, but actually cuBLAS in this case, which is 2 times slower. And the reason why it's 2 times slower because it's making 2 copies of the data instead of 1. And that's why, basically, since bandwidth is the limitation, that's why you have a factor of 2 in this case. But you see here, in this case, if every program was like this, it would be perfect for going to standard because we don't care about exactly what CUDA is, because the only thing that's important is how to move the data. So how do you change this code from CPU to GPU? And I'm going to zoom a bit. Okay. So that is the code. Don't care too much about the syntax here. What's important is here is that you see that now my functions for the GPU doesn't have the for loop anymore. What it is doing is computing I, which is basically an index. And what is basically computing is which data do I need to compute within this huge vector. And then it's doing the computations inside the vector. Okay, I add if statement just to check that I'm not out of bounds, but that's basically the difference where the CPU was here and was this big for loop. So the big difference basically is that the for loop disappears. So basically, each thread is going to execute this, which means it handles one data at a time, exactly like I said before. Yeah, in this case, the index is 1D, but it can be also 2D or 3D, but that's not that important at this level. Okay, that's me. Focus on this. I will come back, I guess. I have a slide later related to that. So how do I compute this index? And so you basically have each thread has its own index here, and then you have the index of the block, and then dimensions of the block. That's allow you to basically know which integer you are, which data you need to handle. And you see each time you have .x, 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 you could also have a .y and .z if you do 2D data or 3D data. That can be simpler for you to organize your stuff like that. But typically it's a bad idea. Well, not a bad idea. You need to be careful when you do that. That's the correct statement. Okay, so this is probably a better way to explain what I just said. So here you have block 0, 1, 2, 3, and 4. So like you can see, it starts at 0. So if you want to analyze this data, it will receive block ID 3, block dimensions, that's the number of threads in a block that you choose technically in advance. In this case, for the example, I put it to 8, and the thread ID is 0, 1, 2, 3, 4, 5. That's why it's 5. So one thing, and I will say it, I guess, at least 3 times in this lecture, and I guess Orion will say it again, and this afternoon you will hear it again. What is super important is the way you read memory on GPU. That's the most important trick, actually, if you want to use GPU efficiently. The first thing that everyone is going to look at your code when you go to GPU is how you read your memory. And what you need is what we call coalesced memory. So what it means is that the thread ID plus 1, in this case, thread ID is 5, thread ID is 6, would take the data memory, which is just next to it. So you don't want that thread ID 6 is reading that memory. That will be terrible in terms of efficiency. But you say it like this, you say, yeah, easy peasy. In practice, that's the main bottleneck of all code we want to put on GPU, is to have that as much as possible. Okay, so the next line, so for when I show you how I changed my function from CPU to GPU, was basically removing the for loop. The next question is, how do you call that GPU functions now from your code? And you have this super ugly syntax. So you have the function's name, and then you have this triple bigger sign, and then you have 2, 3, or 4 arguments. In this case, I stop at 2. You'll see later 3 and 4 arguments, which is the number of blocks that you want, and the size of the block, the number of threads within one block. So this number has a maximum typically around 2000, 2048, and you want that number to be a multiple of 32, because you want to have a multiple of the warp. And this number, obviously, you basically take the amount of data you want to analyze, you divide by this number, that's basically give you that number. And then again, discrete syntax, and then basically the argument that you want to pass. Okay? Okay, so now that you know the basics, let's do the full code now. There will be 7 steps. First, initialize the GPU, that's trivial. Initialize data on the CPU, that's very simple as well. Allocate memory on the GPU, move the data to the GPU, run finally your code, move back the result, and do some cleaning. So nothing too complicated in a way. Let's go step by step. So can you read, or should I zoom here? You can read? Yeah? There as well, you can read? Yes. 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 Or you have on your screen, so that's perfect. So basically here, I'm initializing data on my CPU, use the same malloc as before. And for initialization for the GPU, I'm using QInit 0. So technically, you don't need that function. So you see a lot of codes might not have it. My only advice why I suggest you to put these functions is just so that for the profiling of your code, otherwise the first CUDA functions, it will call that automatically for you. But then you will see your first CUDA call takes 3 seconds, and you might not realize why is that actually. So that is basically for the profiling, it's clear, okay, it's initializations of the GPU, which takes around 3 seconds normally. Okay, so the next part, the important part, is to do allocations of memory on the GPU. So you exactly like on the CPU, you are using malloc. Here you use CUDA malloc. So nothing too complicated. The only thing is that CUDA decides to have always all the CUDA functions should return an integer, which is basically a status code. So if the allocation succeeds or not. So all the CUDA code should return an integer, while in C++, normally the normal malloc returns the pointer that corresponds to the allocation that you did. So now, since they want to keep that convention that return an integer, they need to have two arguments, the size basically of the data you want to assign, and basically a pointer of a pointer now. That's why the x is a pointer, but you pass here the address of the pointer. So that's the conventions. You might like it or not, anyway, it's like that. Yes, this is important. So you don't need to do that, obviously, but at least in these lectures, every memory that sits on the GPU will start by D underscore. And that's also the advice that I will advise you to do for your code, to have a conventions at least, it doesn't have to be that one, but basically to separate what is inside your CPU and what is memory inside your GPU, to basically have a conventions of naming. So how to move data from host to device? You have the CUDA mem copy functions, which I found a bit ugly, but again, it's not my choice. So you start by saying where you want to write the data. In this case, the data dy, so the pointer on the GPU. Then the origin of the data, that's the host pointer, so that's easy. Then the size, and then what I don't understand why you need that is the directions of the transfer. Why I don't understand is that if you want to copy in the other directions, it's still first where you want to copy the data and the origin. So in a way, I would say the compiler should be able to know which data is where. Therefore, I would say that this is useless, but you need to do it anyway. Yeah, transfer from host, from CPU to GPU are not super fast. I mean, they are fast, but not super fast. So one way to speed up the computations, if you initialize everything to 0, which is typically the case, you just could mem set the pointer 0 and then the number, the size basically. That will set everything to 0 without needing to have actual transfer. A nice trick that I like is using what we call pin host memory. So it's a different way that the memory is handled on the CPU that allows fast memory transfer between CPU and GPU. So it's in order to assign, to basically, so instead you replace your malloc for the CPU part by CUDA malloc host. And now, of course, this is returning a pointer on the CPU, but it's basically formatted exactly like for the GPU and has the faster memory transfer. The downside is, of course, it's this malloc takes a bit more time on the CPU to do that a normal malloc, but that's not relevant in general. The second downside is that this type of allocations is limited, so you have less space, I mean, less memory available than the full RAM, basically. Okay, just try that's if it helps, it helps. So now next step is to execute the kernel. So we already seen this syntax with these triples bigger and smaller with the number of blocks and the block size. You can see here that I pass the pointer now on the GPU, my number, and then of course the size of my problem. So as I said, you will see a syntax with also 3 and 4 arguments between this. So at this stage, I will just tell you it exists. So the third one is to allocate shared memory, so memory within a block, which is common to all the threads. That can be sometimes very useful, sometimes needed. And this for streaming, but that's in order to basically multiple computations synchronize and stuff like that. We will not cover that today, actually. One thing, you probably have seen it already. So in the definitions for my kernel, I was putting an __ global in front of it. And that's to tell basically the compiler that these functions can be called from the CPU and GPU. So it's important for the kernel that you call from the CPU with __ global. If you have a function that is only call from for the GPU that you can put underscore device. And technically, if your function is only for the CPU, you can do also underscore host, but that's the default, so there's no point to put it, except if you want to be explicit. Moving back the result, that's the CUDA mem copy, destinations, source, and now you have to change this device to host instead of host to device was before. And basically freeing all your pointer as usual. Okay. Okay. So that's the full code. It's basically all the steps I've seen before in one slide. So how to compile? Typically on clusters, you do a module load CUDA, then NVCC. Like on CPU, you typically have to specify which type of GPU you want to target. There's of course a default. And typically you put the architecture which is correspond to the GPU you are targeting. But if you want to be able to target older GPU, then you can specify 7.0 is quite old now, but you have 8.3, I guess, is the latest. That depends, of course, on the GPU you want to target. If you put a high number here, it will not run on old GPU, and obviously. And then you can pass basically, so instead of GCC, you use NVCC, but you can pass any C++ flag for the CPU part of the code. So like O3, linking to your library for your CPU code and stuff like that. Everything you can put as usual. Yeah, one thing which is start to be less true now, but it's still problematic. One good advice is to put all your GPU functions into a single file. Optimizations, it starts to be better with CUDA 11, but still not super great, I would say. If you put some functions in one file and some function in the other file, the code will compile no problem, but your performance will be degraded actually. So you will not realize that you can keep the memory on the register and will move all the memory back to the main memory and then do a lot of data transfer for nothing. And then if you put magically all those functions to a single file, then you get a huge speedup. So that's my advice. Of course, if your code is super large, it might not be possible, but try as much as possible, I would say. It's just the compiler are not smart enough. I didn't test after CUDA 11. It was starting to progress with CUDA 11, but after that, I didn't test. So obviously, the GPU is not always the fastest. So this is the code exactly SaxPy that I've seen before, that I was using before, running for, I don't know how many pounds, but basically you can see here that it takes 2 seconds, while it takes less than 1 second on CPU. So basically the issue is that we have too many data transfer. I have to know the most of this initialization of the GPU, which is around 3 seconds, as I said before. So actually here you spend the time to initialize your GPU, then use it super fast, but basically during the time of initialize your GPU, your CPU was already done. So of course, now if I'm doing more and more computations, so I do 10 times these computations 100 times, you see that my GPU is going to start. As I said, if we don't do enough computation on the GPU, the CPU is better. And here, basically, the time to initialize my GPU is actually quite large. Okay, I think I speak for a long time, so that's good to have some questions. So what do you need to have an efficient GPU executions? Do you need a lot of data to offer parallelism, a code in CUDA, a good memory access pattern, and a lot of string multiprocessor? Looks like we see answer on live. Okay. Let's check what I did answer when I create. So you need to offer a lot of parallelism. I said that a lot of times. I'm quite happy that you all get it. A good memory access pattern, that's actually the most important point. Coded CUDA, technically not. You can use OpenACC, you can use SQL, and that will also typically, in some cases at least, be able to have good speed up or very good speed up. A lot of string multiprocessor is not really efficiency, I would say. That's for you, the most string multiprocessor you have, the faster your code is going to be. But it's not really efficiency in this case. It's just you're always interested with your code running super fast. Okay, so now let me focus a bit more about memory. I already said, tell you that memory was super important on GPU. Told you the main trick that what you need to do is what we call coalesced memory. Let me go a bit more in detail. So what are different kinds of memory available on the GPU? So there are two types of memory. I would say there's the memory inside the streaming multiprocessor, so close to the computations, and the one which is outside. So inside, actually the fastest memory available is what we call the register. And that's basically really the memory associated to the thread. And that's the memory that's doing the data for your computations. So when you have something in register, it's super fast. So that's the fastest memory. It is thread specific, but the amount of memory here is super, super small. I don't remember exactly the size, but very quickly it's kind of impossible to have enough memory with register, I would say. That memory is super small. It's not really a problem in a way, because if you need more, basically it's going to the cache L1. The cache L1, which is here actually. So it's also extremely close. But you go to one level of cache already. The second type of memory is actually the shared memory, which in this plot is represented here, which is also relatively close. Basically, if you don't use shared memory, it will be used as cache L1 as well. So it will not be wasted in a way. One trick we typically use is we know data that are important for your computation that you're going to use a lot of times. And by putting them in shared memory, because you can force data in shared memory, then you can ensure that they're always in cache, basically. So even if you don't need shared memory for the meaning of shared, you can put in shared memory for each thread, but so that you ensure that they are always in cache. So that's an option how to trick for efficiency shared memory. So shared memory is also limited amount, is limited to the block. Okay, underscore share is the prefix on how to call it. Okay. Yes. So outside the streaming multiprocessor, you technically have the L2 cache as well. But the biggest memory that you are going to use is the global memory. So that's where, I mean, the bandwidth is huge, close to the terabyte per second. So the bandwidth here is super large, but the latency is also terrible. So I said in the beginning, that's the GPU. You have super large bandwidth, but super large latency as well. So this is actually where you put the data. So when you, in the previous example, I was doing a CUDA malloc, that's where the memory was assigned. So that's in global memory, which is outside. So it's not the fastest memory available, but you have a huge amount. So that's up to 80 gigabytes of global memory. So the important point is that when you access the data from global memory, you never access a single element. You always move to the streaming multiprocessor, what we call a cache line. A bit like the cache line that we're discussing on Tuesday for OpenACC actually. So when you want to have one data, what you do actually, in you have an animations, well, not with animations, but yes, you move the full cache line to the L2 cache. And then it's available to move higher away to L2, one cache and register. So that's why you can go back to the coalesced memory access. Since you do for one data the full movement to L2 cache, if your other thread read basically in the same cache line, then you have high efficiency because you don't need to transfer from this to this anymore. If your second thread was asking here, it will make a second transactions basically, and you have to pay a second time the latency of this memory. Okay, so where is it? I mean, if you have a vector that's relatively easy to handle, you need to be, of course, very careful with 2D. Okay, right. I thought I was adding to something. So if you have not 1D index, but if you have basically an array, then you need to be very careful how to access your array. And I will come back to that actually later. So now that we've seen all the memory, I'm asking them to order them by latency, which was the most reactive or the fastest to the one which is the slowest. We have L1, shared memory, global memory, L2, RAM on CPU, and register. Okay. So register, L1, L2, shared memory, global memory, and RAM. Actually, shared memory and L1 are actually the same latency. So those two are exactly the same. So this is, I would say, a correct answer. While flipping those two would be a correct answer as well. Register is the best, then shared memory, and L1, which is basically the same, L2, global memory, and then RAM. Okay. But the one you really manage, I mean, in practice, you can really manage shared memory. You need to try to manage a bit register, because that's where if you put a lot of pressure, that will dig away your efficiency, basically. So you want to make the stuff in register as small as possible. And that's how you design basically your functions. Shared memory, you have control. Global memory, that's where you put your stuff. And from here to here, you manage as well manually. And you need to try to minimize this as well. Okay. Yeah, this we have already said. So now imagine you have an array, and then I have, in this case, 4 kernels, 1, 2, 3, and 4, that going through my array in these directions. So that means at the same time, I'm handling M00, M01, M02, and M03. And then I'm going to the next step of my computation. So I'm computing those 4, and I'm computing on those 4, and I'm computing on those 4. That's what I mean by this. That's the access of each thread is doing a line in basically in my array. So this array is converted in terms of memory. So if I put that in memory and what it is physically on my global memory, it's now in that direction. So now you can see that when I'm starting to do these computations, I need to have M00, M01, M02, and M03 available. Now, here I'm going to have M01. I've not done any computation, so I need to ask it for global memory. So that is going to take me a cache line with typically 32 bits. So I assume here that my cache line is here 4. And then, but before starting my computations, since those 4 are doing the same computations at the same time, I also need to have this element available. So I need to do a second call actually to global memory. That takes a huge latency again. Same for the third, same for the fourth, and so on. And then now I have all my data available, and I can start my computations. So you can see here the fact that basically I'm reading my element not next to each other. I'm basically increasing my latency by a huge factor. And then after that, I can restart the computations, and I probably need to redo it again because I didn't have enough space on L2 to store the old stuff, so I need to restart at each iteration, probably. But this is quite inefficient. So in this case, what I need to do is to change my code to work in the other directions, so that each thread is handling a column instead of a line. Is it possible or not? That's depending on the code, obviously, but that's basically the main idea. Because if I do that, my 4 threads need now these 4 yellow bricks, which are next to each other. So I can only do one call to the global memory to move everything to have it available. Now everything is accessible. I can do my computations. And then I can restart doing the next call and doing the computations. And in practice, what's happened is actually more close like this. I'm doing the first call. The GPU is already doing the second transfer when I'm doing the first computations, and I'm doing the second computation. And in that case, I might not even need to wait, or much less, basically. So that is why this mode, what is in this case called as memory, is super crucial, because you will you will avoid a lot of latency to access your data. skip a question. So very simple questions actually. So in general, to have coalesced memory, can you just trust the compiler? You need to change your data structure of your code, or basically you don't need to do anything if that's automatic, which is kind of the same as one, I would say. But yeah, so that's the annoying part, and that's where you need to work both for single instructions, multiple data, and for GPU, is to change your code to have this coalesced memory access. And that is the key point really for GPU, and that's actually the key point also to get single instructions, multiple data. Because for single instruction, multiple data, you also need this coalesced access, otherwise the compiler will refuse to do it. So typically, there are two types of structures, I would say. There is a structure of array and the array of structures. So what it means here that when you do object-oriented programming, you typically do an object which contains a float A, a float B, a float C, and an integer. And then you typically do array of those objects, right? That's not, I would say, my normal, at least, myself way to think. I think about an object, and then I'm making a list of an object, which is great and works super well on CPU because everything is close together in a way, at least non-vectorized CPU. But then your data management, in a way, in memory is written like this. So you see all your floats A are here, all your floats B are here. And of course, if you want to run on GPU, that means they are not coalesced because typically you want to access the same A at the same time, right? So that is super bad for a GPU or for single instruction multiple data, but it's a natural things to do. I mean, I found that quite natural. What you need to do is basically move this index inside the structure. And that's why it needs a lot of work. That's why it's a bit boring. But if you do that, then your memory pattern is now nicely colored. And then you have super efficient access for GPU and vectorized CPU. So vectorized CPU is the same as single instruction multiple data. It's synonym. Might be confusing for mathematicians, but that's the same name. Okay? So that's the typical work that if you want to move a CPU code to a GPU code, is basically move this index inside, change a lot of for loops and stuff like that as well. Okay. So coalesced memory is not always possible. Let's take, for example, you want to transpose a matrix. Then, of course, what you do, you read your matrix in the correct way, but then you write in the wrong way. So there's no way, if you want to transpose a matrix, that you are fully coalesced memory access. It's just impossible. Because one way is the line and one way is the column, you cannot choose. So the way to use is to use shared memory as a cache. So you can transfer your memory to the shared memory and have all the non-coalesced access from the shared memory. So that's what I said before. The shared memory is typically the place where you put tricks. Is that when you know that you have access in terms of memory which are not optimal, try to move from global memory to shared memory, because there it's much closer, basically, because it's as fast as L1, so it's super fast. And then you can do access which are not optimal. It's still not optimal, but in some cases you have no choice. So there are other types of memory available. Constant memory and textured memory, that's basically something I've never used so far, actually. They will be put at a different place. That's typically read-only type of memory. And then there's one thing which is nice that I said I hinted a bit before. So for the moment, I said I have my CPU memory, I have my GPU memory, and I'm handling the movement myself with this CUDA copy, right? What you can also have is to create this kind of memory access, which is CUDA malloc manage. And then you pass, of course, you receive a pointer as usual. But this time, this memory is not bind to the CPU or bind to the GPU. And you don't tell anything when you move the data, and you let the compiler know when he has to do it. So that's probably in the future, if a future like that exists, is that we have the same RAM on CPU and GPU. This will be ideal in a way, because then you don't need to move anything. But that is the way you basically let the compiler decide when to move the data from CPU to GPU and back. you can try, I would say. Typically, I like to manage my data myself, but okay. Okay. One last complications. So there's you can see that compared to CPU, GPU, they have a lot of stuff, I would say, to learn. Not all are super critical in a way. I mean, this one is not the most critical one. But you need to know, I would say, much more than the CPU in order to make some code efficient. Which is the bad point of GPU, at least the status right now. Why am I not plugged? Right now. Okay, not sure why it did that. So the shared memory has a system which is called a bank system. So the data are actually not available in all. How can I say that? So you have your shared memory, which has technically a 32 bank, and your data is in one bank. So if you need to access the data, you need to know in which bank your data are. So the way to know it's very simple. It's just a modulus operation. So that's a no-brainer, I would say. But why is it important? That's like a bank, you have basically a queue, right? And you can only serve one data at a time. So imagine that you have your 32 threads that all going to access data in your shared memory. And if thread 0 is asking bank 0, thread 1 is asking bank 1, basically in one operation you have all your data. So that's a no-brainer. So this is, in a way, what coalesced memory is, obviously. And that is best performance. Now, as I said before, you can also use shared memory when you have non-coalesced access because it's super fast. But you still have a price, in a way, because if, let's say, you have your access element, but you jump one, which we call a strike 2, you have thread 0 going to ask on bank 0, thread 2 is going to bank 4, thread 3 on bank 6, and so on. And that means at some point, some threads are going to go back to bank 0. So we have some banks which do nothing, but the most annoying point is that some banks are handling 2 data. So they have to answer one after the other, so you basically are slower. So there is a price as well for the shared memory if your data are not coalesced. But this is still much better, obviously, than if you need to do the same kind of stuff with the global memory. So it's still much better to do it at the memory bank level, so the shared memory, but you need to know that there is a price. Yes? You can, but then it means you use twice the shared memory. No, that you cannot. No, what you could have is to say, oh, my memory size is twice bigger, and then you can do it. Well, it's probably you're going to use it, but later in the code, right? Because otherwise, if you never use it, then basically your data will not be look like this. We only have the black dots, right? So if you are using it like that, it's probably there are a reason in a way, I would say. And of course, you can, if all the data are going to the same back at the same time, that's problematic. So there is tricks, maybe you will see this afternoon, I don't know. When you typically also sometimes add a padding basically in your memory so that they spread on all the banks. So that's typically a trick that is used. So that your bankers, instead of your data, you add a fake data at some point so that they are shifted by 1, and therefore they spread more on the bank in a more fair way. So that's one trick you use. Okay, I'm running out of time, and anyway, this is you're going to cover this afternoon. What I want to say, maybe in 2 minutes, you'll see that later. So we have discussed today there are 2 types of limitations of your code. You will have the memory limitations and the computing limitations. At some point, if you ask too much computations, you will not be able to do it. So you will see this afternoon this kind of plot actually, where it says how much you use efficiently your memory. So you see here, I'm really using a lot of memory, but basically I'm never doing any computations. So that means my code is heavily using bandwidth, and actually I'm never doing computations. So that's what we call a memory bound computation. And that is going to happen quite often. So you have the second case, which is already much better in a way. So here you're doing a lot of computations, and you don't use that much the bandwidth. Which, okay, maybe you can do to cache more computations so that you do a bit less computations and transfer a bit more in this case. That in this case, you can try to compute a bit less and basically caching more, using more the memory in order to gain efficiency. While here, basically, what you need to do is probably recompute stuff multiple times rather than transferring it multiple times. And the worst case scenario is this one, which is typically when you start your GPU optimizations where you start with, if you have a code that doesn't compute at all and doesn't use the memory at all. And what the code is actually doing is basically waiting. And that means you are latency bound actually. So you are waiting basically the data to arrive from your CPU and from your memory to your actual computation. And that means you typically need to provide more parallelism or try to have basically more warp alike, I guess. Right? Let's just have the time to say it basically. So the number of warp active at the same time, that's depending on your block size, obviously, but also depending on how much resource available for the warp. Because each warp which is called active, that doesn't mean it's run, it's just that it's in memory. And therefore that can be run at any time. But of course, if any warp uses a lot of memory, let's say, the number of warp which is active will be relatively small. So in this case, if you have 4 warp which are active, and at some point warp 0 needs to have a lot of data coming from global memory, it takes a lot of time, what the GPU is going to do is to run instructions on the other warp. And therefore, this is efficient. But if your warps use much more memory, and that puts more constraint, and therefore only 2 warp can be active at the same time, can be put on memory at the same time. As soon as warp 0 takes a lot of time, warp 1 will run, but at some point will also need to wait, and therefore you waste computation time. So it's also something which is super important to track and try to optimize, and that means reduce typically the memory that you use, is how many active warp you have at any given time. And for that, in the profiler, you have plot like this. So in this case, that's the number of registers used per thread. And basically what it tells you that if you, for the moment, you are something, I can't even read the number, or whatever the number here is, and you see that if you are succeeding to reduce a bit the memory on this thread, then you can double basically the number of warp active. And that's more, that will help you to parallelize the code more easily. And that's the same, if you remember at the beginning, I said, we don't care how many trucks are in transit. And that's what this plot is, basically. The number of trucks in transit, the more your truck are in transit, the faster your code is going to be in general. Not always, but yeah. But this is only. So here, for example, one trick that we can use is also to force the compiler to assign this number of registers. Say, I don't want you to use more than register, so you go a bit more on cache by forcing this function to go here. So you go on cache because your thread technically needs that much memory, but then you have much more warp, and then you can, you typically check that. This is the same for the block size, so typically it doesn't matter too much. And here for the shared memory, so how much shared memory you can assign or not. The more memory you assign, the less space you have for multiple warp. Okay, so let me go to my conclusions. Perfectly on time. So GPU is for a massive amount of computations, so for high throughput. And basically, one of the main goals is to hide the latency. So everything is going to be slow to transfer, small clock speed and stuff like that. But you have a lot of data. What you want to do is try to hide that latency as much as possible. You have various types of parallelism. So the thread is 1 unit. Warp is 32 units that are doing exactly the same computation for a given time. And a block is basically a collection of warp. And that is how you scale your computations. Various type of memory. Try to, minimize the amount of global memory that you use, basically, and the transfer that you need to do. So you need to try to be as light as possible in terms of memory, which is not simple. And the main message is coalesce memory points and structure memory. Yes?
Just one question about the last bullet, less memory with an array with how to have
yeah.
As we saw, structure of arrays.
I'm confused now, so I will go back to.
No, it's correct. It should be structure of arrays.
Structure of array, yes. Yeah, I wanted to be sure. I say, oh, maybe I did a mistake. So what is important is to have this. In some cases, in some code, with full flexibility, what we have done is to create an array of structure of array, which combine those. I mean, you basically have index here and here, so that you can size basically according to your hardware. But that's a bit on overkill, I would say. Okay. Any other questions?